His master thesis presentation, and the presentation will be about 20 to 25 minutes. After that, there will be some questions from the public. I hope there will be some questions. After that, we will be in a closed environment together with the committee for 1 hour for questions and exam. Then you will go out of the room, we will decide the grade, and finally we come all together to announce the grade. So I hope you will be patient to go through all of this. And I invite Ruben to start the presentation.
Could you I'll translate in Italian for ora Ruben farà una presentazione riguardo la sua tesi di 20-25 minuti, poi il pubblico sarà libero di fargli domande per 5-10 minuti, dopodiché andremo con la commissione in una sala dove privatamente faremo domande per assicurarci che Ruben sia un bravissimo studente per un'ora, alla fine della quale gli daremo un voto e ci sarà una proclamazione pubblicata a tutti. In bocca al lupo.
Okay. So I see that some of you people here are wearing glasses, and I know that at least 2 of you here are wearing contact lenses. And some people really dislike it, taking them out and putting them in there every day, or for your glasses, looking everywhere and finding them on top of your head. And so some people actually go to laser eye surgery to get their vision corrected. And what laser eye surgery is they use a laser to etch away some of your lens on your eye, so that they correct for the flaws that you would have glasses for. And in order to do that, the doctor usually takes a picture of your eye. Here on the left you see a patient with her head in the machine that measures it. And on the right you see a doctor who takes a picture of the eye over here, and he makes a reconstruction of the shape of your eye, and so that they know exactly where to cut away parts of the eye to correct for your vision. So in order to do this laser eye surgery, it is very important to have a very correct representation of your eye with this machine. Now these machines usually work with a Scheck-Hartmann sensor. And the way a Scheck-Hartmann sensor works is like this. Here we have an eye, and in blue you see a laser beam that is directed on the back of your eye. This laser illuminates a point source which will emit light back out of your eye. And this emitted light is then captured by the Scheck-Hartmann sensor, here shown with the lenslets and with the CCD. The image that will be formed is something like this. If you have perfect eyesight, you will see small dots. However, if you need glasses, you will have a distorted pattern like this. Knowing the positions of the spots for the perfect eye and knowing what the eye actually is, you can use this information to get back the reconstructed aberration, or actually the shape of your eye and what is wrong with it. Since the 1980s, a conventional least squares method has been used for this spots to aberration reconstruction. However, there is a known problem with this, and that is called the crosstalk, and this crosstalk makes this reconstruction worse. So therefore, in 2014, Dr. Janssen has published in the Journal of the Optical Society of America the paper called Zernike Expansions of Derivatives and Laplacians of the Zernike Circle Polynomials. In this paper he introduced a new algorithm that does this wavefront reconstruction with the Scheck-Hartmann sensor, but it should not present this crosstalk. However, this is a mathematical paper, and it gives the mathematical basis, and it has never been implemented in an experimental setup. It has never been verified in experiments. Therefore, for the past year, I have done research by comparing the conventional least squares method to this new Janssen's method. And in the past year, I've come to the conclusion that, for instance, for this eyesight reconstruction, Janssen's method would be better than the conventional least squares method. I do have to note that eyesight reconstruction is not the only application of this Scheck-Hartmann sensor, but today in my presentation I would like to guide you through my findings by the hand of this, by the hand of this laser eye surgery model. I would like to show you what I found in my research. And I will convince you that Jansen's method is a better method by the hand of 4 points. First of all, I will show you that the methods were rigorously tested on a modified Michelson interferometer setup. Afterwards, I will show you that Jansen's method performs equally well in optimal circumstances, so nothing is lost when we're implementing Jansen's method. Afterwards, I will show you that Jansen's method performs better when fewer Zernike powers are fit. This is where this crosstalk comes into play. And last of all, I will show you that Jansen's method suffers aliasing earlier than the least squares method, but I will argue that from an engineering point of view, this should not matter. So first of all, let's get into how the methods were tested. First of all, I would like to show you how Jansen's method and how the least squares method actually work, and how they can reconstruct the wavefront from a Shek-Hartman pattern. Afterwards, I will show you that an interferometer setup with the spatial light modulator is used. It is used to remove aberrations and then add controlled aberrations. After this, I want to show you that both methods were individually optimized for the center position and radius on the beam, and I will show you why that is necessary. And last but not least, I want to show you that I've defined the error as an RMS error between the added and the measured wavefront. What we see here is a side view of a Shek-Hartman sensor with these lenslets here and a CCD camera on the bottom. And these lenslets are placed in the focal, the focal distance away, such that if a flat wavefront comes in, it will create a spot pattern. Now, if there is an aberrated wavefront coming in, like with a real eye, the spots were moved, you see that this aberrated wavefront W creates spots, but not in the normal positions with a flat wavefront. And the way that is done is the wavefront is averaged over the lenslet, and the average slope of this wavefront makes the spots move in X and in Y position, because it's a 2D sensor. Now, we know this displacement, delta X and delta Y, but we want to get back to this original wavefront W. The way we do this is we know that the derivatives of the wavefront, the Cartesian derivatives in the lenslet positions x0, are related to the spot displacement from its flat spot position. And it's also related to the radius of the laser beam on the Shek-Hartman sensor, so the total radius. And it's related to the focal length of the lenslets. Now please keep this radius in mind, because it will come back later when we're talking about the optimization. So taking what we know, we want to expand the wavefront W in terms of Zernike polynomials and their Zernike coefficients. And these Zernike coefficients is the thing that we want to know. And what we've measured is basically this derivative of the wavefront. Here, in this infinite series, m is the azimuthal order, and n is the power of the Zernike polynomial. If we take the Cartesian derivatives of this wavefront W, we can express this again as an infinite sum. And this is a set of equations that we can approximate with linear algebra. So taking this set of equations, we can form a vector S where we put all our information that we gather from the Shek-Hartman sensor. This is the derivative of the wavefront in spot positions 1, 2, up to n spots. And if we then define our wavefront Zernike coefficients A also as a vector, we can set up a geometry matrix with the Cartesian gradients of all the Zernike polynomials that we want to measure as such. And then we can retrieve our wavefront, or our Zernike coefficients, as a generalized inverse of this geometry matrix. And we do a matrix vector product with this generalized inverse and our spot displacement vector S. Now this is the least squares method, or the very conventional method. And I will show you now how Jansen's method differs, because the first thing that is different for Jansen's method is that we are using complex Zernike polynomials, and in general also complex Zernike coefficients. In Jansen's method, the derivatives of this wavefront are added and subtracted in this way, and also a least squares fit is made, this time not with the derivatives of the Zernike polynomials, but with the complex Zernike polynomials. And from this fit, we gather our pseudo coefficients beta plus and beta minus. Now we add these beta plus and beta minus up together to get a phi and m, and we define a new coefficient C and m using the Kronecker delta. And in the research of Dr. Janssen, he has shown that we can find a natural minimum least square solution for our coefficients, complex Stirling coefficients alpha, as such. It is important to note that our coefficients alpha, they scale with beta plus n plus 1. So if we fit with 8 powers of Zernike polynomials, we only retrieve 7 powers of coefficients. And this will be important later when we're looking at fitting higher order aberrations to our wavefront sensor data. But for now, keep in mind, so if we fit 8 powers, we retrieve 7 powers of alpha. So now that we know how the least squares and the Janssen's method work, I want to show you the experimental setup on which the experiments have been done. First of all, a laser is shown through a Faraday rotator to prevent the laser from being damaged by reflections off of optical surfaces. It's passed through a filter to lower the intensity of the laser beam, and a half-wave plate is used to orient the polarization of the laser beam with the SLM. Afterwards, the beam is expanded using 2 lenses, and an iris is placed directly after the second lens to get a flat phase profile over our beam. This is then reflected to this is then propagated to a beam splitter, where one arm shows the reference mirror, which is a very flat mirror, and the other arm shows a spatial light modulator. Now, due to time reasons, I cannot exactly tell you why, but the spatial light modulator will be under an angle, and I encourage you to ask me why this is later at the end of the presentation. But it's under an angle because aberrated light and unaberrated light needs to be separated. And this is done by focusing the unaberrated light on the plane of an iris, but not in the center, so that it's physically blocked, while the aberrated light is shown through the iris. A last lens is used in order to collimate the light again. And after this, there is a Scheck-Hartmann sensor with, denoted with SH, and an interferogram camera. This interferogram camera can be used to directly see if the aberrations that are added correctly. Here we see a typical Scheck-Hartmann pattern, and I want to show you that it is important that the radius and the center position are optimized. If you remember from the theory, the radius was an important part of these derivatives of the wavefront. And here on the left we see the actual sensor with the spot positions in blue, and the optimized center position in orange, and the radius in black. And as you can see, this is the optimized position. And if you're closer to the screen like me, you can see that for the radius, it is slightly different for the least squares method and Janssen's method, because this spot is excluded. And you can also see that the optimized center is just placed a little bit to the right. And this gives us the optimal reconstruction for both methods. So it's seen that the least squares method and the Janssen's method need to be optimized separately from each other to give the most fair comparison possible. After this, I want to show you why or how I defined this RMS error to find this optimum position. And here I've shown you one of the experiments that I've did, where on the left we see my reference aberration that I've added with the spatial light modulator. And in the middle and on the right we see the least squares reconstruction and Janssen's reconstruction. And it can be seen that the least squares reconstruction and Janssen's reconstruction, they look very similar. Now, if we define our RMS error as a point-by-point difference between the reference phase and the reconstructed phase phi rec, and if we take the typical RMS error for this, we can see that for the least squares method it would be 0.244, and for Janssen's method it would be 0.241. So very similar RMS errors are seen for very similar phases. Now that I've shown you how I've done my work and that I've done my work rigorously, I want to show you that Janssen's method performs equally well in optimal circumstances. Now, first of all, optimal circumstances has to be said that it means that we're fitting 8 powers of Zernike polynomials to our data. This optimality is taken from a rule of thumb based on literature. And first of all, I will show you that when we're adding lower power aberrations, both methods perform equally well. And afterwards, I will show you that when adding higher power aberrations, the least squares method works better. This is another typical experiment that I've done, and this space pattern is generated with a maximum of 5 Zernike powers. And we can see that the reference, the least squares method, and Jansen's method all look very similar visually. And this is also seen in the RMS error. Actually, personally, I cannot see any visual difference. The only thing I know is that the RMS error is slightly lower for the least squares method. If we take a higher power of Zernike aberrations, for instance 6, in this experiment I've added the 6th order quadrifoil. You can see that the least squares reconstruction and Jansen's reconstruction are very, very similar, and it is again shown that they have almost similar RMS error. However, if we introduce higher power aberrations, such as this one, here on the left we see an aberration that I've taken from a microscope objective, so this can be typically seen in microscope objectives. We see that the least squares method and Jansen's method actually differ quite much from each other, but also from the reference. From each other they differ because here in the bottom right corner we can see that the least squares method has a darker blue, so there's a higher, you can see a higher gradient if we go from here to here, which is typical of higher power aberrations. While for Jansen's method, this peak is lower here, and this valley is higher, so we don't see the same sharpness in the wavefront reconstruction. And this can be explained because, as I've said during the theory, that Jansen's method retrieves only 7 powers of aberration coefficients when we are fitting 8 powers of aberrations, while the least squares method can retrieve 8 powers of aberrations when we're fitting 8 powers of Zernike. And so this last power adds part of the reconstruction that makes at least this part a better reconstruction. It should also be said that still they are not very similar to the reference, because here in the middle a peak is missing from both methods, so we can see that still not the complete aberration is resolved for neither methods. Another example of this is another lens aberration where the same can be seen. Here is the same, or is a similar gradient in the aberration, which is better resolved by the least squares method than by Jansen's method. But now let's get to the good part, to the crosstalkless wavefront reconstruction. So I will show you that Jansen's method performs better when fewer Zernike powers are being fit. I want to show you first of all what this crosstalk is, and that Jansen's method does not show this. And afterwards I want to show you that statistically Jansen's method is better at fitting or at estimating A and M using n plus 1 Zernike powers. So first let's get to this crosstalk. A typical experiment where crosstalk is present is an experiment that I've done such as this one. Here I've added defocus and the 4th and 6th power spherical aberration. And here in this graph we see how these coefficients are estimated, which is on the y-axis, and on the x-axis are the amounts of Zernike powers that are being fit. It can be seen that when fitting only 2 or 3 Zernike powers, so when retrieving only the first 2 or 3 powers of Zernike aberrations, the least squares method overestimates the defocus present, while Jansen's method is much closer to the reference value, to the actual value of defocus present in the system. Now this is very typical for crosstalk, because crosstalk basically means that when taking the defocus coefficient and not fitting high enough powers, it will see these higher power aberrations. You will see that back in the estimation of the coefficient, but it's wrongly estimated, so it gives you back a worse estimation of the complete wavefront than it actually is. And it can be seen that that Jansen's method does not see this influence of the higher powers of aberrations being present, because it's always close to the reference value. Now, I wanted to look at this also statistically. So what I will show you is I've taken the difference between the estimated and the actual value, and I've put all that data of all the aberrations that I've measured together, and I've shown this in a logarithmic scale, where I've taken the difference between the actually added aberrations and the estimated coefficients using k fitting powers. And these fitting powers, I've used n plus 1, n plus 2, and n plus 3 fitting powers. And so that means, if we go back one slide, that I've looked at the difference between the reference value and the defocus coefficient, for instance, for using 3, 4, and 5 fitting powers. If we look at the box plot showing all the data that is gathered, it can be seen that this difference, the median of this difference for the least squares method in blue, is significantly higher than for Jansen's method in orange for n plus 1 fitting powers. It can also be seen that the outliers for the least squares method are higher, and that in general this whisker of the box plot is higher, denoting that there are more gross or bigger errors present in the least squares method than in Jansen's method. What also can be seen is that using n plus 2 or n plus 3 fitting powers, this difference is completely gone. And this n plus 1 fitting powers really shows that this crosstalk is still present, and that Jansen's method does not suffer this crosstalk. Now that we've seen that Jansen's method does not suffer this crosstalk, I want to show you that Jansen's method suffers aliasing earlier than the least squares method, but I also want to argue with you that this should not be a problem from an engineering point of view. Again, we will look at this experiment of subsequent Zernicus, and here I've shown you on the x-axis again the amount of fitted powers, while on the y-axis I've shown the reconstruction error, the RMS reconstruction error epsilon. And around this optimal reconstruction power 8, we see that both methods are minimal. And here in this inset I've shown you just an enlarged version of what is going on beneath here. But we can also see that when we're fitting not 8 but 9 powers, that the RMS error is already increasing a little bit for Jansen's method, while for the least squares method it stays similar, or it's even going down a little bit. And the biggest increase we see here in Jansen's method when fitting 12 Zernike powers. Now this is due to aliasing, and this extreme jump in reconstruction error tells us that it's giving back bogus rather than actually estimating these coefficients correctly. And a similar jump for the least squares method can be seen using 13 fitting powers, which is one later than Jansen's method. And I've seen this in basically all the experiments that I've done, that this initial jump is higher or is earlier for Jansen's method than for a least squares method. Now, for laser eye surgery, when we go back to our example, it should not be a problem, because when it is used in such a machine, if you are engineering your machine and you are putting in a Scheck-Hartmann sensor that needs to use more fitting powers than is optimal, I would say that you're making an engineering mistake, and you should either fit less powers or you should switch your Scheck-Hartmann sensor so that it can actually estimate those coefficients correctly. In conclusion, I've shown you that that my methods were tested on a modified Michelson interferometer setup. I've shown you that Jansen's method performs equally well in optimal circumstances, and is therefore there's therefore no loss when implementing Jansen's method. I've shown you that Jansen's method performs better when fewer Zernike powers are present, so when this crosstalk gives an effect. And I've shown you that Jansen's method suffers aliasing earlier than the least squares method, but I also argued that from an engineering point of view, this should not matter. And therefore, I think that Jansen's method should be introduced in every new laser eye surgery machine. Thank you very much.
Question is if you would dare to have an operation with your algorithm. Questions?
Yeah.
Oh,
So first of all, on behalf of my liquid lens, I have to tell you I'm very happy that you chose the rotationally symmetric example at the end for your analysis. But I have another question, and that was about your first comparisons of the reference least square fit and the Jensen algorithm.
Mm-hmm.
They look slightly asymmetric to me, especially the axis. So if you go to the first one of these examples, or the one with 6...
Do you remember the slide number?
Not exactly. I can just tell you that it was very colorful.
Was it this one?
Yes, this
Yeah.
one looks perfect. Exactly. So your scale goes from minus pi to 0.9 pi. So is there an offset in there on purpose, or is that just a plotting thing?
Yeah. So your question is why does it not go from minus pi to pi? You want to say. To make all these pictures, I've made a script that takes the nearest integer, or no, not integer, but 0.90 integer that is above the maximum value of any values present, so that it gives a, well, not always symmetric scale, but it always gives it from minus 1.1 or minus 1.2 to 0.9 or 1.0. So it's an artifact of the script that I've made rather than deliberately
so
introducing
no
this.
asymmetry in there that you introduced for whatever reason.
No. I've this experiment I've only introduced fifth order coma, and I think that one of the methods gave us a slight, maybe was estimated some tilt. Some tilt was estimated, therefore lowering the lowest point slightly. I think I wouldn't. I won't be. I'm not sure why, but it's how my scripts chose basically the minus and the minimum and the maximum values.
Question?
Yeah. On slide 23, you show these distribution plots.
Mm-hmm.
With increasing maximum Zernike power fitted.
Yeah.
And if I look at those plots, I actually see that they improve if you plot more Zernike powers.
Yeah.
They seem to, by factor 2 or something, improve. So does this go on? Can you just keep on plotting more powers, and does it then keep on getting better?
That's a good question. So basically, your question is, because we see this slight decrease in error, and so increase in reconstruction quality, can we just fit more and more until we reach 0, basically?
Basically.
The answer, sadly, is no, and that is due to this aliasing. In this plot, I've shown you also an increasing amount of Zernike powers being fit. And in general, for the least squares method, you see that around this optimal number, it does go down. But if we keep increasing our Zernike powers that we are fitting, we do see a jump. And that is due to aliasing. So you are not seeing the difference between higher power and lower power aberrations anymore. And so you're mixing them up and you're estimating wrongly at that point.
So if I understand correctly, you should pick the amount of, you should pick the power in which the aberration matches with the actual aberrations that happen, the actual mathematical order of aberrations.
Yeah. You want to estimate the powers of aberrations that are present in your system. So for laser eye surgery, that would be lower powers usually, because mostly you are suffering defocus, which is second order. And for the eye, 8 orders would be good, but if you're looking at very turbulent media, another implementation of the Scheck-Hartmann sensor is also in atmospheric turbulation measurements, because when you're looking at stars, the light goes through the air, and the air adds aberrations, and in your telescope you want to correct for those, and then you might want Scheck-Hartmann that can fit higher power aberrations, because those are generally higher power as well, depending on the weather conditions.
Can you go back at 20 or the previous slides? Why you show just the difference between the coefficients and not the ratio? I mean, not the ratio, but the difference divided by the coefficient. Because right now I don't know which coefficient you took Well, I'm more interested
Yeah.
on the percentage maybe of change or.
Yeah. So let me grab the slide in question. This one you're aiming at, right?
Yeah.
Yeah. That's a very good question indeed. And so the question is, why am I just using the absolute difference and not the percentage difference between what is actually there? Yeah, that's a very good question. I have thought about this, I think too late, that I should also look at the percentages, because it came up to me, but my thesis was already being compiled, and so I think it's a very good thing to look at actually, because it might introduce unfair peaks for the least squares method, for instance, because if we go back to this one, we see that the scale of overestimation for defocus, well, the defocus present is 4, and it's estimated 50% higher. But that is, because it's 4, it's a factor of 2. And so that might be a lot worse than, it might introduce unfairness in the comparison. I agree with you.
You also mentioned that the SLM is put at an angle. Could you explain to us why?
Yeah, of course. And luckily I prepared some slides for this. So what we see here is a schematic overview of an SLM. And an SLM consists of a reflective silicon backplane and electrodes on the top and on the bottom. And in the middle are liquid crystals. And liquid crystals can be aligned using a different voltage that you put over those electrodes. And the alignment of the liquid crystals determine the phase difference, or determine the optical path difference that the light goes through, because they are a birefringent material where if the light shines through from one direction, it sees a different refractive index than from another direction. So in that way we can accurately add these aberrations. But as you can also see in this picture, these electrodes are pixelized, and there is a little bit of dead space between the two pixels. Now this backplane is reflective, and so light that hits these liquid crystals does get the retardation from the optical path difference, but light that goes in the middle is not aberrated. And so if we would not remove this, we would see a mixture of aberrated and unaberrated light, while what we want to see is only the aberrated light. And so what you can do is you can put your SLM under an angle and introduce an opposite angle with the SLM as a tilt aberration to account for this angle. So you're basically, with the liquid crystals, you're putting it back straight again. You're adding this distance. And so it was only a few degrees, but that was enough for a long distance lens to focus, to split the focuses of these both beams enough so that they can be separated. Does that answer your question?
Thank you.
Last question. Yes.
Your research showed that the method of Janssen is better than the method of, I forgot which other method. Least squares, yeah. Do you think there are other perspectives than the technical perspectives that your research showed, that some people won't introduce this in the eye surgery?
Yeah, so you're saying I've shown you only the good parts of Janssen, the technical parts.
Yeah.
And the question is, are there any other downsides or perspectives that are that have not addressed? Well, the good part about these two is that they use exactly the same data. So the physical system doesn't have to be changed, only the algorithm for the retrieval of those aberrations needs to be changed. A thing that does need to be taken into account is that Janssen's method is in general slower than the least squares method due to the fact that complex Zernike polynomials are used. This makes it about 4 times slower. And so if you want to if your phase aberration that you're measuring is changing quickly, you want the quickest method possible rather than the best method possible. So it does differ from application to application which one to use. And that is why I've shown you today for the laser eye surgery, because I know it's about precision. While if I would have shown you a telescope and showing that the aberrations of the turbulent air, I wouldn't have come to the same conclusion, basically.
Thank you.
Oh, let's think again. And